they're going to give introduction to the study of the gamma function. Sometimes when we deal with integrals, they give us non-usual values which can be expressed in terms of functions. So such integrals that we don't solve in a conventional way, they are called improper integrals, and we have specially two types of improper integrals which can be represented as the gamma function, and the second case is the case of the beta function, which will be seen in the next video. Now, what is a gamma function? Now, gamma is represented by this symbol here. This is not the symbol of a square root or cubic root. This is just a symbol of gamma. So just go up and then right. So if we have, for example, gamma of n, so it is defined as a function which obeys this integral from 0 to infinity of e raised to minus x raised to n minus 1 dx. And now this n is a natural number, which means n is greater than 0. So if someone says gamma of n, what the person is implying is this, for this is the definition of a gamma function. Now, the gamma function can be expressed in this way, but it can also be expressed in a different way. For example, in this case, say for example, we want to make a different consideration. Take x is equal to t squared, right? So this means that derivative of x is equal to 2t dt. So in this case, what you're going to have is from 0 to infinity, our integration of e raised to minus x, but x is t squared, so it's going to be minus t squared, and then you're going to have x raised to n minus 1, and x is t squared. So t squared, but that 2 is going to multiply n minus 1, and dx is 2t dt. So this is going to be equal to, okay, now this 2 is a constant, comes outside. I'm going to have here from 0 to infinity e raised to minus t squared, and then I'm going to have here t raised to 2n minus 2, and this t here is going to multiply, so we're going to have t raised to something into t, so you just have to add 1, same base, just add the powers. So this is plus minus 2 plus 1 and dt. So this is going to give us 2 from 0 to infinity of e raised to minus t squared of t raised to 2n minus 1 dt. So this is the final result we get from this. Now, this means that the same expression gamma of n can also be represented as integration from 0 to infinity. We don't have to be using, here we have to put 2, this expression, but we don't have to be using t every time. T was just another variable, could be n, could be not n, could be h, could be any variable, could even be x. So in general terms, we're going to say 2 integral from 0 to infinity of e raised to minus x squared. We're just calling it all as another variable, in this case x, okay? It doesn't mean there's an equivalence with this one, it just means that it's a general way we can call it, not a definition we're giving, of x raised to 2n minus 1 dx. So these two forms, this and this, can be used as the definition of a gamma function. Properties. Now, property number 1. The property number 1 says that gamma of n plus 1 is equal to n gamma of n. Now, how do we prove this property? It means that if you have a gamma of a given number plus 1, you're going to have just the gamma of that number and gamma of that number. Now, let us try to understand exactly first how we got this result and why this result is very important for us. See, to prove that this is the truth, let us take a limit here. Okay, we're going to take limit when some variable k tends to infinity. We're going to here put it like this. Now, we know that gamma of a function is expressed by integral from 0 to infinity of e raised to minus x, and then we're going to have here x raised to n plus n minus 1. This is n minus 1, n minus 1, right? But in this case we're dealing with n plus, okay, let's keep it like this, minus 1, and then it's going to be dx. This is how usually the definition is, but for gamma of n. But our case is gamma of n plus 1, right? So this means that our limit now changes. We're going to have here k then into infinity, open bracket here, 0 to infinity, and then we're going to have here e raised to minus x. Now this definition is only applicable whenever you have gamma of n, but in this case not gamma of n, is n plus 1, so it means that we're going to have here x n minus 1, which is from the formula, but because we have this plus 1 here, we're going to have here another plus 1, and then it's going to be dx. So this is how it's going to be. So we can just simplify this and simplify this. Now from that point what we're going to get is this: limit when k tends to infinity is this. Here I have 0 and here we're going to have infinity, and then it's going to be e raised to minus x, and this is going to be x raised to n dx. Now we have to find this integral, the value of this integral here. If you remember from the video, the methods of integration, we have here one function which is a function 1, and here have another function we can call function 2. Function 1 and 2 don't have any relationship. This function is exponential and this function here is a power of x. So to solve this kind of function, what we're going to use is substitution by parts. Substitution by parts, also called UDV, right? So how do we do it? Now the formula for substitution by part is integral of u dv should be equal to uv minus v du. Okay, but we have to know what is our u, what is our v or dv, and all of that. And for that we have some rules. We saw that we have a rule called ILate. It can also be leaped, it can have different name, but this is just the sequence of how things go. Inverse trigonometric, logarithm, algebraic, trigonometric, and exponential. In this case here we have algebraic. Algebraic means x raised to something, and we also have exponential. Exponential means whatever thing raised to the power of x. So the first thing we found here as we go in this direction is a, which is algebraic. This means that this portion is going to be our u, right? So u is going to be x raised to n. Okay, so and then the other part, which is this second function here, is going to be our dv. So dv is e raised to minus x dx. This is dv. Now this here is a function which you have to differentiate. So du is equal to nxn minus 1, right? And this is dx. And this one here, it's already differentiated. You just have to integrate it. We have to find v. So v is equal to the integration of this. As we know, integration of this is basically taking whatever the constant is multiplying this variable here, put it as dividing, and then keep the same expression. So this is going to be e raised to minus x divided by minus 1, but divided by minus 1, same thing as saying minus 1. And in this case, because this is the integration of this, we don't have to put dx. So we have found u, du, dv, and v. Right. So with that, what we can do, we can now replace saying gamma of n plus 1 is equal to limit of k tending to 8 of this. Now this was our original function. Now it has to be divided into these terms, uv minus vdu. Now what is our u? Our u, we can now put it here as the first part. Our u is going to be x raised to n, and our v is going to be minus e raised to minus x. This is our first part minus the second part of the function, which is integration of v, which is minus e raised to minus x du, and our du is our n raised to x n minus 1, and all of this is dx, and then we can close our brackets here. Now continue with this. We can do this. This part of the function, or this part of the expression, can already be solved. Okay, so here we're going to have what? Limit of k, we don't have to integrate anything else here, then tends to infinity of this. Now we're going to have here x raised to n, this minus comes here, we're going to have here e raised to minus x, and then we can do this. This means from 0 to infinity. Solving this first part, it's supposed to be minus, but we have minus here inside, so it's going to become plus, right? And then this n is a constant, so it can come outside, so it's going to become n, and then you open here the integration from 0 to infinity. But actually, because we're dealing with these limits here, you don't have to put 0 to infinity here. You can just put the constant k instead of putting infinity. So this is 0 to k, not infinity. Okay, so 0 to k. Then we continue writing this. It's going to be e raised to minus x, and then x raised to n minus 1 dx. Okay, this is our conclusion. Now, substituting this part here, taking first, replacing first all the x's with infinity, and then making minus, replacing all the x's with 0, this is going to give us 0. If we replace all the x's with infinity, then make minus all the x's, replace it by 0, it's going to give us 0. So this means that this limit becomes limit when k tends to infinity of 0, because this is going to give us 0. You can also do this to say that this all leads to 0, plus n, and then here we're going to get 0 k e raised to minus x n minus 1 dx, and then it goes like this. Fine, this is 0, don't have to write it again. Now, instead of keeping writing limit here, I want just to apply this value of the limit here to the value which the limit is tending to. So this can be also written as is equal to, because I'm now replacing whatever I have k with the value of k, which k is tending to, I don't have to write limit again. So this is going to become n, and then it's going to be 0, k is going to be replaced by infinity, and I'm going to have e raised to minus x raised to n minus 1, and then dx. But this whole expression here, which we got as our result, is equivalent to gamma of n. So this means that we're going to have n gamma of n, which proves the property number 1, which is gamma of n plus 1. So gamma of n plus 1 is equal to n gamma of 1. Now, why is it important? This is important because if you keep on expanding this property, if you have, for example, gamma of n plus 1 is equal to n gamma of n, it means that if you keep on expanding this, you're going to reach a situation of factorial. Say, for example, you're going to be given, let us say, 6. What is the gamma of 6? Right, now if you're given gamma of 6, in this case it means that our n in this case is equal to 5. So it's going to be 5 plus 1 to be 6. So this means that this is going to be equal to gamma of 5 into gamma of 5. Now, as you reach this point here of gamma of 5 gamma of 5, you can know that because here we have gamma of 5, it actually means that this value here is n plus 1. So it means that it's 4 plus 1, which is going to give us 5, which means that 4 is our n, which can come outside. So we can have here 5 into 4 gamma of 4. Right, now this 4 here inside can also be treated as 3 plus 1. So if you do this for 3 plus 1, what you're going to get, applying this property, 5 into 4 into 3 gamma of 3. And we're going to keep on going. We're going to keep on going until you find a situation in which you're going to have 5 into 4 into 3 into 2 into 1 gamma of 1. Fine. Now this, it's almost close to factorial now, because gamma of 1 actually is equal to 1. This is our next property. So this means that it's going to give us 5 into 4 into 3 into 2 into 1, which is equal to 5 factorial. So gamma of 6 is equal to 5 factorial. Now the next property I said that gamma of 1 was equal to 1. How? This is the next property. Gamma of 1 is equal to 1. Okay, we know that the formula for gamma function is this. Okay, 0, and then I'm going to have the infinity, and then e raised to minus x, and then x raised to minus 1, and then this is going to be dx. Okay, now we're given here gamma of 1. It means that instead of n here, it's 1. So what I'm going to put is gamma of 1 is equal to 0 to infinity, and then next part of this is this. E is raised to minus x doesn't change, but n changes because n now is 1. So it's going to be 1 minus 1, and then dx is going to be equal to gamma from 0 to infinity of e raised to minus x. Now this is going to be x raised to 0, which is equal to 1, so therefore it disappears. Dx 1, we don't have to write it here, and this is the integration we have, right, from 0 to infinity. Now to do this, how we can do? Come here, we can take limit. We can say limit k to infinity of 0 to k e raised to minus x dx, in case we don't want to work with the limits of we want to work with this integral here, or we can simply just solve this, which is what we're going to do. So we have here e raised to minus x, and then this is bounded limit. You have 0 and you have minus infinity. The property says that you have to divide by whatever is multiplying x. So what you're going to get here is gamma of 1 is going to be equal to e raised to minus x divided by minus 1, right, from 0 to infinity. So this is going to be equal to, this actually can be said as minus e raised to minus x, and then we're going to write this from 0 to 1. So this is equal to, not to 1, this is 0 to infinity. So now first we have to replace all these things by the infinity, right? So this minus can come outside. We're going to have here e raised to minus infinity minus e raised to 0. Okay, now e raised to minus infinity is 0. Is 0, and then now we're going to have here minus and minus are going to become plus, and we're going to have here e raised to 0. Now e raised to 0 is equal to 1. So this proves our second property. Gamma of 1 is equal to 1. Fine. Now combining these two properties, we are safe to say that gamma of n plus 1 is equal to n gamma of n. As we saw by the expansion of the given problem, this would be always decreasing like this, n minus 1, and then again I'm going to have n minus 1, n minus 2, and then n minus 1 minus 2, and then you are going to keep on going, and this is going to lead to eventually our n factorial. And notice that this n is whatever the value was in the gamma that was given minus 1, because the function was gamma plus 1. Fine. And the last property you're going to see in this video is that if we're solving something and then you're going to have, for example, gamma of 1 by 2, this can also be represented as the root of pi. This is important in calculations. This is not gamma of pi, but this is the root of pi.